In this first video, I'm going to be giving you an introduction to transforms and systems modeling. I'm hoping to set up the big picture so that as we move through this class, you can understand how each thing we learn fits into the big picture and how useful this knowledge is to us as engineers. The world that we live in is incredibly complex, and it's full of all kinds of complicated interactions between machines, people, and other kinds of biology, forces of nature, physical and chemical elements, all interacting with each other. This world is far too complex for us to try to understand the whole thing all at once with all of these complex interactions. Because the whole world is too complex for us to understand all at once, instead we divide up the world into systems. A system is a single, smaller part of the world that we can analyze all by itself. For example, we could isolate just the car by itself and analyze its behavior independent of all of the other effects of the car being in the world. Now, of course, even the car itself is not that simple. Each system is itself made up of many other subsystems. In this example, the car has an electrical subsystem. For example, the ignition, the spark plugs, and the more complicated electrical system that allows you to have cruise control. The car also has a suspension subsystem that is mostly mechanical and consists of things like springs and dampers. The car also has an internal combustion engine that is both a mechanical and a chemical subsystem. Each of these individual subsystems could itself be considered its own system and could be analyzed independently. So a system can be defined in different ways depending upon what your goal is in modeling the system. You might define your system as a large piece of the world, such as the entire car, or you might define your system as a very small piece of the world, such as the suspension of the car. But no matter how you define your systems, all systems have a particular characteristic in common. What every system has in common is that every system has at least one input and at least one output, each of which is a kind of signal. A signal is a quantity that changes over time. The properties of the system are what determines how the input signal becomes converted to the output signal. Now note that these signals could be electrical, mechanical, or a combination of both. Signals can also be other things like biological or chemical, but we're not going to focus on those since this is a class that focuses mainly on the mechanical and electrical aspects of engineering. You should also note that each system might have many different possible input signals and output signals. When you are analyzing a system, you get to select which input signal and output signal you are most interested in. I'll show you an example of that now. We choose the input and output signals to be things about the system that we are particularly interested in. For example, with the car, we might be particularly interested in the comfort and safety of the passengers riding in the car. So if we are analyzing the car's suspension system, we might choose the output signal to be the forces on the passengers. Remember that a signal is a quantity that changes over time. As the car drives down the road, the forces on the passengers will change as the car hits bumps in the road. Therefore, we might choose for the input signal the force on the car from bumps on the road. So in this situation, the input signal to the car might be the forces on the tires exerted by bumps in the road, and the output might be the forces experienced by the passengers sitting in the seats. The input signal is converted to the output signal here through our system, which is the suspension of the car. Of course, this car has many other inputs and outputs that we could also analyze. For example, the driver of the car is producing an input signal by pressing on the pedal, and the car has an output that would be the car's velocity, or its acceleration, or its position over time. We could choose any of these things to be inputs and outputs depending upon what we're interested in figuring out about the car. So in this example, the suspension system of the car is converting the input signal, the force on the tires from the bumps in the road, into an output signal, the forces experienced by the passengers riding in the car. The way that this system converts the input signal into the output signal can be represented mathematically with a kind of an equation that's called a transfer function. The transfer function tells us the ratio of the output to the input. The transfer function typically has in it variables that have to do with the system. For example, in this case, we would probably see the letter K representing the stiffness of the springs in the car suspension. We would probably also see the letter B, which typically represents the amount of damping in the system. We would also typically see the letter S, which is the variable in this equation, and it accounts for the change over time. We'll go into the meaning of the letter S much more in depth throughout this class. For now, let's take a look at the usefulness of this transfer function. Knowing the transfer function of a system allows us to do, in particular, three particularly important and useful things. The first useful thing that we can do if we know a transfer function is that we can predict the output of the system for any given input. For example, let's suppose we know the transfer function of the car's suspension. With that transfer function, we can predict how bumpy the ride will be given a road with bad washboarding. In other words, we can use the transfer function to put an input that represents a washboarded road, and we can calculate the forces that the passengers will experience over time. The second useful thing that we can do with a transfer function would be to figure out what kind of input will give us some specified output that we want to achieve. For example, let's suppose that we know the transfer function of the car engine, and that we found this transfer function for the input of the amount that the pedal is pressed, the accelerator pedal, and the output is the forces experienced by the passengers, or let's say the acceleration of the car. In this case, we could calculate what signal through the accelerator would give the passengers a smooth, non-motion sickness ride. This is the kind of a thing that you would want to do if you're trying to build a car and that can be programmed to drive itself, a self-driving car. This is the kind of operation that we often want to do in robotics or in motion control. We want to find the transfer function so that we know what input signal to program our microcontroller to give the system in order to get the system to behave the way we want it to behave. This is what we need to do in all kinds of automation tasks. Thirdly, with a transfer function, we can figure out ways to change the system itself in order to give a better input-output relationship. For example, if we know the transfer function of the car's suspension, then we can simulate the forces the passengers will feel on a bumpy road. And we can simulate a change in the spring constants of the suspension to get a smoother ride. Remember in the example of the transfer function that we saw earlier, some of the variables in the transfer function were parameters of the system, the spring constant K and the damping B. If we know the transfer function, we can figure out what values of K and B will give the passengers a nice ride even when the road is bumpy. This kind of an operation is very important when we are doing system design or machine design. So with these three important functions that we can do if we know a transfer function, how do we find this all-important transfer function for a system? In order to do each of these three important operations, we need to know the transfer function of the system. We find a transfer function by modeling the system. Almost everything that we are interested in modeling can be modeled with differential equations. That makes sense since we know that the input and the output signals are both quantities that change over time, and differential equations are the kinds of equations that describe how things change over time. Once we have a differential equation that describes the system, we can then convert the differential equations to a different form that's easier to work with by using something that's called a Laplace transform. The Laplace transform gives us the transfer function in terms of a variable s, which represents an integral when it is in the denominator of a ratio, and it represents a derivative when it's in the numerator. This form of a transfer function makes it easier for us to look at the relationships between the input signals and the output signals, and it allows us to do the three important operations that we talked about earlier. In this class, we're going to be looking in particular at three aspects of transforms and systems modeling. In part 1 of the class, we're going to primarily look at different kinds of inputs and outputs. By doing this part of the class first, it will help us start out by getting some practice seeing how transfer functions can be used. That will then lead into part 2 of the class, in which we'll learn how to develop the models for different kinds of systems, including mechanical systems, electrical systems, and complete electromechanical systems. Finally, in part 3 of the class, we'll look more in depth at this Laplace transform operation and a little bit at something else called state space modeling. By the end of this class, you should be able to find the differential equations that model an electromechanical system, simulate the output behavior given a specified input to the system, use the model to design better systems, and use the model to figure out what kind of input will give you a desired output. In other words, you'll be able to control the system.